I'm interested in the question of epistemic virtues, their diversity, and the epistemic fears that they're designed to address. What I'd like to do here is to talk about what we might be afraid of, where our knowledge might go astray, how we gain, by epistemic I mean how we gain and secure knowledge, and what aspects of our fears about how that might misfire can be addressed by particular strategies, by particular strategies, and to see how that's changed quite radically over time. The place where Lorraine Daston and I focused in the study of objectivity, for example, was in these atlases, these compendia of scientific images that gave you the basic working objects of different domains. Atlases of clouds, atlases of skulls, atlases of plants, atlases in the later period of elementary particles. These are volumes, literary objects, and then eventually digital objects that were used to help classify and organize the ground ideas or the ground objects of different scientific domains. And so proceeding in a somewhat caricature way through the argument, it went something like this, that in the periods you might schematize by being 1730 to 1830, and these dates are arbitrary and overly precise, you had a desire above all to find the objects that were in back of the objects that we happen to see, not this clover outside the boardroom, half moth-eaten and half sunburnt, but the plant form that existed behind that. That's what Goethe meant when he talked about the Urpflanz, or analogously the Urinsekt, or other forms. It seemed obvious, the advantage of that. The fear was that you would spend your time looking at particular defective clovers here or there or other places and not understand that they were unified under a particular form that was the reality behind the curtain, so to speak, of mere appearances. Or when William Cheselden in 1733 hung a skeleton and looked at it through a camera obscura, you might say, oh, he was looking to draw that particular skeleton, but he wasn't. He was trying to use that and then correct the errors, the fact that it was too fat or too thin or a cracked rib. Or when Albinus said, I draw what I draw and then I fix the imperfections, it was because it seemed obvious that the images that you would want of a skeleton, a flower, an insect, or whatever it was not the one for the skull that belonged to me or you. It was the skull that belonged behind all the particular skulls that we might see. So there's a fear of the multiplied, variegated skulls or clovers or clouds that we might see, and the antidote to it was taking a strategy of drawing something abstracted from that was supposed to lie behind any particulars. And so Goethe would say, don't draw, I never draw any particular thing. Now, there was a particular kind of person who was appropriate to doing this, and that was the genius. And in the 18th century, it was recognized that it was fine for an Albinus or a Goethe or a Cheselden to make that kind of argument. What happens in the 19th century is that begins to proliferate. And when everybody starts writing down or drawing or painting the objects that they thought should be there, and they start to clash, there's a new kind of problem that's faced by the conflict of the myriad depictions of the heart or the skull or the plant world or the natural world or crystals or other things. So the response to that was in part a swing the other way. So the epistemic fear was of this contradictory multiplication of representations, that each of which purported to be the Urpflanz or the equivalent in other domains. But the response was to say, no, we want a mechanical transfer of the world to the page. And by mechanical, it doesn't mean just the levers and pencils. It could mean any kind of thing, including chemical-based photography. In the 19th century, mechanical meant all of those procedural developments. So the new goal, and this was labeled objectivity, for the first time in a sense that's continuous with the modern sense. When Descartes uses a term like objective, he means more or less the opposite from what we do. That's another story. But starting around 1830, coming from a mix of literary and scientific sources, people start to talk about this as the mapping of the clover to the page, whether it's tracing or rubbing, or eventually in later years, photographic representation. In any way, to minimize our intervention. If Goethe, Cheselden, and Albinus were maximizing our intervention because they were the sort of people who could part the curtain of experience, the 19th century said, we want to minimize that because we don't trust the multiplied number of scientists in the world. We want to know what was actually there, the skull of this person in case 23 in the Museum of Natural History in Berlin. And so that became a different kind of response to a different fear that had swung the other way. Now, when you look at things, then now you're in a new kind of problem because there are lots of different skulls, each of which is correctly or isomorphically represented, at least that's the ambition. And people began to say, well, how do we know when a skull has a tumor and it's a normal variation? So then they started to have atlases of normal variations. But you can see how this leads to a kind of regressive problem that could go on forever because the space of possible variations of skulls just within this room is pretty large, and you extend it over all of humanity and all of time, and it's extremely, extremely large. And so it became very hard to work. The way that doctors used these atlases was to say, here's normal, here's the range of the normal. If I see something that doesn't look like that, it's pathological. And what actually got me interested in this in the first place was these atlases of cloud chamber and bubble chamber images more in my field, in particle physics. And there, it was used in a very interesting way. This is a literary form that the physicists borrowed from the doctors. I mean, physicists don't like borrowing from doctors, but they did. And they said, though, that if you see an image that departs from the range of the normal, what you have is a discovery, not a pathology. And so the bubble chamber scanners, in the dozens at Berkeley or CERN or wherever it was, would study these compendia and then alert the up chain of command till it got to a Louis Alvarez or somebody else to say, we've discovered something. So one way what then began to happen was people began to say, okay, well, we actually have to use judgment, that this pure mechanical objectivity is proliferating like crazy with all of these variations. We need to know what is actually a misfiring of the apparatus or the environment and what is actually a real effect. So the people making magnetograms of the sun said, look, we could print mechanically and objectively what we get out of our machines. But you wouldn't be able to tell what's an artifact of our machines, but we know. Not because we're geniuses. They didn't say that, but the implication was not because they're geniuses, but because we've trained. And that kind of trained judgment became a new kind of objectivity then. So you could say, I've corrected this, I've taken an MRI, but I've fixed this artifact that has to do with the way the machine did its Fourier transform, and we know leads to all sorts of problems. There were cases where a whole bunch of back surgeries were done because of an artifact produced by the doctors missetting the machine. And so that became then, so people began to worry about how you would train people to recognize artifacts and to do it in a way that had a kind of, you could follow as a course or as a procedure. And for instance, there's a famous atlas of electroencephalograms that said, look, you do our course for several weeks, and we can train you to distinguish, grand mal, petit mal seizures and various other things, not because you're a genius, but because we can train you. Now, you might say, we tried to make this purely procedural, algorithmic. We tried to do a Fourier transform on the signals. It didn't work. It's actually a complicated problem. And they said, but we can learn how to do it because we humans are particularly good at this kind of pattern recognition. So that became a mantra in the 20th century, that you have all these atlases that explicitly extolled the human capacity to learn judgment, to actually become trained experts, not innate geniuses, of which there's 1 or 2 or 3 or 5 per century, but we can train all the people that have to look at electroencephalograms to make these kinds of distinctions in a way that was repeatable and therefore objective, but not mechanical. We don't know how to do that, they said. This is in the 40s and 50s and 60s. We don't know how to make it purely algorithmic. And the same was true in stellar spectra and other astronomical problems. You could, long before you could classify stars by a procedure or an algorithm, people became very good at classifying them by looking at the spectra and making judgments. So these are shifts that in response to fears, these are epistemic virtue, to answer your question again, is the response. It's the Rx to the DX. The diagnosis of the problem was some fear, and these are responses of procedure, of judgment, of mechanical transfer to those difficulties. Now, this leads to a question that I've been thinking about in the AI context, which is, so there's a current project that I'm involved with in various ways, the Event Horizon Telescope, and they're trying to make images of very distant objects like supermassive black holes and other objects in the sky. And one of the problems is that the data is extremely sparse and noisy, and you have to extract an image from it. So there are two problems, and I think of them, one of them is the spring of Narcissus problem. The spring of Narcissus problem is that you can't just print what you see because you don't see anything. So you need to say, it's like if I gave you a bunch of points and I said, draw the best curve through it, you would rightly say to me, that's not a well-posed question. You can say, draw the best straight line through it, easy peasy. Every ninth grader can do that. You say, I want the best circle or the best hyperbola, whatever it is, then you can solve the problem. You need to assume something, and then you can get information out. And these images have that character. You have to make some kind of Bayesian assumption, some prior, and then from that, you can actually create an image. But that leads to the problem of Narcissus. The worry is that you might impose so heavily your prior assumption about what you would see that you would see it when it wasn't there. It's like Narcissus looks into the spring and sees his face. But if you don't impose any prior knowledge, then you have the opposite problem. You have the problem of the helm of darkness. You don't see anything. You can't extract anything. You have this sparse, noisy image. So this is a battle that, so then the question is on this collaboration is, how do you get an objective image? And there are various strategies that they've taken. They're very interesting. For instance, one of them is to divide this team of about 120, 100, 200 people on this collaboration, but the imaging teams are divided into groups, and they work under utter secrecy from each other within the collaboration, and they produce their images and compare them. Another is to vary the priors and see if and then the question is, have you varied the priors enough? Would that give you an objective image? Now, there's another possibility, which has been suggested by AI. The AI folks have said, for instance, in an analogous, well, not somewhat analogous problem, which is that the Space Telescope has got a huge number of galaxies, more than the astronomers could cope with to try to classify and understand. So one of their first moves was to make this into a kind of public game. And there are hundreds of thousands of people who do this thing called Galaxy Zoo, where you sign up and you're given images, you take a training program, you take a test, and then you start classifying galaxies. This is elliptical, this is not, so this is not a galaxy at all. And but people didn't like, some people didn't like that, and they said, let's use AI. We can train the computer to classify these galaxies. And so they begin to train the computer to classify the galaxies. And then the question is, using these the neural net kind of arguments, they said, okay, so now we've classified these things. It reproduces things we know. We think this is great, but we can't interrogate the program as to what it's doing. It's got this obscurity that we've talked about here before. So you now have a different kind of problem. You've gained opacity and capacity at the same time. You can now classify a lot of things. You can show it overlaps in the restricted domain where you've got experts have classified, and it gives the right answer, but you don't really know what it's done. And then there's in this domain of AI imaging, there are lots of interesting papers where people start to talk about the AI and attributing it a kind of human capacity. They say it mislearned, or it started to act pathologically here. It's put stripes on. It found a little bit of striping on the snail, and it covered the snail completely with stripes, made it look like a zebra snail. And they start to say, well, we're trying to figure out what it's thinking here. What is it doing? And this an attribution of kind of purpose and humanity to this program, partly in virtue of the fact, but that it seems to be acting making human kinds of errors, but then you can't ask it what it's doing, and that's become a big issue. So that's one of the struggles. Is you'd like the AI to take over some of this task as a way of solving the objectivity problem, but then in response you gain an opacity problem, and that happens in a lot of domains. In my contribution for the book, I talked a little bit about algorithmic sentencing, where the judges wanted to sentence people on their objective likelihood of committing another crime, but then either because of proprietary secrecy of the company that makes the algorithms, or because the algorithms are so complicated that they can't unwind them, they don't either know or won't be told how it's making this decision. And is it using criteria that would violate our norms, like you live above 125th Street in Manhattan, and so we're giving you a higher sentence, which is just a proxy for race. So, these issues, that's in the moral, political, legal domain, but in the epistemic domain of the sciences, there are analog questions that you might ask. What kinds of criteria are actually being emphasized in this? And so that's, I think that one of the, What is the alternative to this opacity, or what is it? We know what the gain could be. It could increase our capacity. It could give us a kind of objectivity beyond human judgment. But it costs us in what we can interrogate. But suppose that it worked. Suppose that it was we were completely happy with it. Would that be enough in the scientific applications of AI? I don't mean what you buy on Netflix or Amazon. I certainly don't mind not knowing the algorithm by which it tells me I might like a movie if I like the movie. But this suggests this question of whether even good, excellent prediction in the scientific domain would satisfy us. And here, I just want to end with a reflection that James Clerk Maxwell had back in the 19th century that I thought was really rather beautiful. And Maxwell, just by way of background, had done these very mechanical representations of electromagnetism, gears and ball bearings, and really with strings and rubber bands. And he loved doing that. But he's also the author of the most abstract treatise on electricity and magnetism that used the least action principle, and that that doesn't go by the pictorial, sensorial path at all. So in this little, very short essay he wrote, he said, some people gain their understanding of the world by symbols and mathematics. He says others gain their understanding by pure geometry and space. And then he says there's some others that find an exhilaration in the muscular effort that is brought to them in feeling the force of objects moving through the world. He says what they want are words of power that stir their souls like the memory of childhood. So you have these three kinds of people. And he says for the sake of persons of these different type, whether they want the paleness and tenuity of mathematical symbolism, or they want the robust aspects of this muscular engagement, we should present all of these ways, and it's the combination of them that give us our best access to truth. And I think that what he was actually talking about in some ways was himself, that this is what he wanted. And if you go back to one of the great Old English origins of the word understanding, Under doesn't mean beneath. It actually meant among. And standing, or standen, was different forms of standing. It's almost like you're sitting in a grove, or standing in a grove of different trees. And I think what he suggests, that the trees is not part, that's my metaphor, and that's not part of the Old English. But, and we see that in other languages as well, like verstehen and so on. I think that sense of being among these different ways of grasping the world, some predictive, some mathematical, some, even something as abstract as a black hole. They're models that use swirling water like a bathtub, around a bathtub drain, to understand the dynamics of the ergosphere. The ability to stand among these different things might be something that we want. And whether we can make use in different ways of AI, or whether AI will only be part of that understanding, seems to me to be known. Thanks.
Thank you. So, Peter, there's one straightforward response. When you say the network is inscrutable, that's a very sort of early, simple version. One interesting thing happening are what are called autoencoder networks, where you force the network through a constriction, and you force it to have a low-dimensional representation after it's gone through this high-dimensional unpacking. And there's been a lot of really interesting results where you then look at these internal representations and find they're interpretable. And so it's a very simple version just to say it's a big network, and the output comes. You can ask the network to help you find a representation. And there are a number of interesting examples of what comes from those.
Yeah, I've seen there are a bunch of different ways of sampling in the space of that can help you. But certainly the people that do a lot of this imaging work find that they are unable to unwind.
But again, what I'm saying isn't sampling. It's something different that's a little more recent, which is as part of training the network, you train the network through an internal constriction where you ask it to find an interpretable representation. And so it's a very different architecture from just you look at the network and figure out what it's doing. It's you train the network to teach you a representation you can understand. And there are very interesting examples of that working.
So I'm actually not, I understand the sense in which you say the networks are inscrutable, but I'm actually surprised that you think people are scrutable. Which is, certainly if you ask somebody why they decided something, they will make up a story. But whether that story has, there's very good evidence that in many cases that story has nothing to do with what actually happened.
I think that's true. But you can sometimes get farther with it. At least that was the hope.
So I would think that that's actually a better hope, particularly if you want to have networks that have the property of understandability, which is the kind of thing Neil was talking about, to actually have AI things that are truly understandable how they made the decision. I think there's more hope of that than there is with.
Yeah, I think there's sort of two orthogonal problems that are getting mixed up here. One of them is how much access does the system have to its own processes, and then the other one, which is actually the sort of scientific problem, is what the system is outputting in some important sense a representation of what's actually out there in the world. So if you sort of think that all of human cognition, or at least a lot of it, is this inverse problem about you've got a bunch of data that's coming and you want to reconstruct what it was out there in the objective world that it was creating that data. That's the central problem of something like a visual system, and it's the central problem of science. There's two different things. One of them is, do you actually understand what the process is that is enabling you to solve that inverse problem? And then the other one is, have you solved the inverse? Do you have something that looks like a solution to the inverse problem? Do you actually have a representation, whether it's accurate or not, about what's going on in the world outside that's leading to that pattern? So, for example,
to answer that second question, though, you have to have some criterion of the quality of the solution, and that's a very well studied thing in classifier theory and so on. There are many measures of the quality of the solution when you decide to basically, cluster things and so on, and so you can kind of pick your measure.
Yeah, but I think
and you can measure how good it is under that measure.
I should say that it's not that people said, "Oh, well, humans make judgments. That's fine." In fact, that's what led in the first place to the development of mechanical objectivity, was that they didn't like relying on those judgment, even by people like Goethe and Albinus, because they felt that it was obscure. And when it began to be a real problem was when it proliferated in the 19th century.
Danny, what was Marvin's line about not understanding something unless you know it lots of different ways?
Yeah.
He had a nice way of saying that.
Yeah.
In your early atlases, we see the power of Platonic thought. I mean, and the extension of Neoplatonism through the late Renaissance.
That's how I think of it. It's a sense that you can find a pure form that lies behind the myriad particularities that we encounter.
So this is Plato's cave, in fact.
So in cluster theory, that's considered a bad algorithm. So that's considered.
What is? I mean, go back to
Neoplatonism doesn't work in cluster theory. So there is one way. I mean, there is a way of representing clusters, which is to, in some sense, pick the center of the cluster and say, I'll pick all the things that are closest to this. Right. The better algorithms, like vector support methods, actually pick a bunch of outliers and say, I'll pick anything that's closer, anything farther out than this, I won't consider in the cluster.
So there are lots of interesting examples. I mean, in the history of classifying images by scientists, there are a bunch of different strategies. One was to take the most perfect extant instance, right? Actually, the best skull. Another was to take the best skull and abstract from that and make it even more perfect, maybe geometrizing it in some way or making it into a perfect harmony of measures. Another was to take an extreme example or an average. They took all, there were atlases that would take like many livers and weigh them all and find the average weight of a liver, and then that became the notion. That's more like your center choice that you were saying. And then in the biological domains, very often they would take the first discovered instance becomes the
that's the type specimen.
The type specimen.
Right.
That's which is even stranger, right?
Yeah, so Harvard, for those who haven't seen it, Harvard has this amazing room of drawers in the museum, and you pull open the drawer, and there's look like little fur pelts, and the fur pelts might be like for a beaver or a squirrel, and it's not a beaver, it's actually the beaver. It is the beaver. All beavers are defined by the beaver. And they've actually become much more important recently because they're now sequenced, and they're used to do genotypes and phenotypes.
So, but you can see that there's a struggle to try to figure out how to make a representation of a class of things that are different. Right?
But I guess what I'm saying is in cluster theory, which clustering algorithms,
take the extreme
clustering techniques. I guess the ones that work less well in practice are the two that you mentioned before, which is pick the one that's closest to the center, or make up an imaginary one that's in the center. Right. Those actually don't work very well.
Right. The first one that happened to be found.
It turns out that the ones that seem to behave the best in practice is something that was not in any of your lists. And I'm not sure if this is ever done in atlases, but it's basically what are called support vector methods, where the support vector is basically the set of things that are right on the edge. And so you define it by things that are barely within the category.
So Danny, I mean, is the measure that you have some kind of objective measure of what the things are that are being clustered independently of the cluster?
Yeah, and that's what I'm saying. And so so
that's the problem that Peter is raising, is when you're doing science, right? You're in this situation in which you're trying to actually do the clustering, and you're trying to figure out what the thing is that's generating the data that you want to cluster.
Your machine
in parallel to
the outline.
It's a much harder
galaxy.
It's a harder problem than say classifying galaxies. Yeah. When you're looking at something and you don't know, like you're looking at a candidate black hole with a surround, and you don't know what it's going to look like. It's different than sort of saying, well, there are three kinds of galaxies. I want to classify them. This one, I know it looks like one of those. Then you're in a much easier
problem. I think
problem.
the problems seem to proliferate off Earth, right? So out of Plato's cave is fine when you can wander around and pick up the turtle or the beaver. But when you're drawing the canals of Mars, you You don't,
Actually,
you don't have the muscular, you don't have the symbols, right? You just have geometries that it turns out you're imposing. You're imposing on the mechanical
I disagree.
artifact.
I actually think Neoplatonism is never fine. And actually,
All I'm saying is, as a historical progression, Platonism works for those people who have philosopher kings and can wander and pick up the beaver. It works less well when you're relying on a telescope and looking at a surface of a distant planet.
But in fact, I think that the reason that this, so if you look at these methods for machine learning, there are, so you're describing support vector machines, where it's a mathematically well-defined process to make a cluster. We have two clusters, and you try to draw the hyperplane that separates them with the maximum margin, which is a good idea, and works extremely well, also in high dimensions. And then, of course, the stuff on the edge of this margin, so the support vector is defined. And then you could also do k-means clustering, which is the other one. You pick a representative example, and you say, oh, we can put these together. And you find that both of them work okay, but of course, there aren't actually necessarily clusters. There's no definition of what a cluster is. Well, these things will have examples that overlap with each other, so you have things that impinge on the other clusters. There is no, abstract ideal cluster that's there. And so you are stuck with, as you said, you have to come up with some reasonable Bayesian prior to say, okay, here's how we're going to deal with this situation. Now, what's wonderful about the current time, about these artificial intelligences, is actually these inscrutable objects, these deep neural networks, which are very good at actually doing these kinds of clustering decisions for reasons we don't know. As I love your quote that we gain capacity and opacity at the same time. And this is true. I mean, this is actually, as you say, this is how human beings operate also. And so we have this nice feature where we admit these artificial intelligences, which we are not going to understand, in roughly the same way we don't understand humans, into our spectrum of models that we're going to trust in order to do things like look at medical images, where are extremely important that we have, in addition to radiologists looking at medical images. We also should say, let's run them by the deep neural network and see what they say too. So I think that it's actually rather nice. We have other artificial intelligences with whom to collaborate. Yes. We don't know what they're doing, but we also have other methods that we can compare, like things like support vector machines and well-defined mathematical methods where we know what's going on, which actually incidentally is what happens in Netflix. What Netflix does is not actually a deep neural network. They have this matrix completion algorithm where they sample it's well-defined mathematically. It's very labor-intensive, but we could walk through it and say, okay, here's what's happening inside your computer exactly, and here's why it works. So there's
one more thing, though, to what you said, which is that actually in many examples, there is an outside way of measuring the quality, which is if you're going to do something with the decision, it's the utility and the success of doing whatever.
It's really cancer or not.
That's right. So there are many systems in which you can say, well, this clustering technique was better than that one because it corresponded more to the way that we use the decision.
That's most useful. You don't know yet what the thing is. It's easier if you have other independent tests. You can say, okay, well, let's go to a higher frequency.
And actually, I think there's a great example of that, which was done sort of by accident with the example you said about the type specimens, which is, basically the grouping of animals in terms of genuses and species and things like that was done by people deciding, well, the important character is, the shape of the jaw or, the number of tailbones or something like that. And what was interesting was that was all done pre-DNA, and actually even pre-necessarily everybody that was doing it believing in evolution. But then when we got the ability to sequence mitochondrial DNA and got some insight into the underlying process, it turns out almost exactly all those judgments were correct. They had picked the correct character and so on. So their clustering method, although it seemed very arbitrary, in fact, exactly reproduced the tree of life.
One way you might rationalize that is that if you're an explorer and you're hiking in the Amazon and you find this turtle and you want to say, well, this is a new turtle. This is a turtle. No one's seen a turtle that's of this species. You would probably not choose one that looked almost like the extreme example of the new turtle that looked a lot like an old turtle. You'd look for a turtle that was pretty different. Yeah. So you're actually prejudiced towards a type specimen that is more distinct than the marginal one might be.
Drawing something that's never been seen before. I'm thinking here of Leeuwenhoek's submissions to the Royal Society, where he's drawing a sperm and he inserts a homunculus.
Right. So that seems to me a kind of early example of what I call the spring of Narcissus problem, right? When you see something like looking for a black hole, no one knows what a black hole is a supermassive black hole, what the form of the shadow is going to be. I mean, there are models, there are simulations, we have some idea, but no one knows. It's not like looking at a known galaxy and then saying, how does this method match up with what we already have seen at not as good radio telescopes?
Yes, something that's misleading in the way we've been talking about this is modern clustering algorithms don't give you true force, they give you distributions. So they get soft clustering, a hard clustering like k-means will miss something really important just over the boundary. Modern clustering algorithms give you distributions of being associated with things.
This is digital versus analog.
Say again?
It's digital versus analog.
Well, yeah, it's probabilistic. So, applied to this, you don't get the image, you get PDFs over families of images. And that's how modern clustering works. And so we've been sort of describing true-false outcomes.
But some of these are designed to classify galaxies one by one into categories.
Right. Yeah. But in modern classification, you don't get the classification, you get the probabilities of associations. And the classifier wouldn't tell you the difference between 4951 and 0, 100 likelihood. Modern classifiers give you the classification, but they also give you uncertainty on top of that.
There's an interesting contrast if you're looking at humans, and especially if you're looking at kids, in that one of the things that people have discovered that's really interesting is if you're looking at kids' categorization, there certainly seem to be some kinds of processes that are doing things in a kind of associative way that are essentially looking for distributions. But by the time kids are linguistically categorizing things, they have something that's this much more essentialist, science-like category, almost like a kind of, it is a natural kind category. So what they think is the thing that you're pointing to when you say something about a dog is actually has nothing to do with any distribution of the properties of a dog. They think it's whatever is the underlying causal category, whatever is the underlying causal set of properties, which is giving rise to some set of data, some set of things that you're perceiving, which could turn out to be completely wrong. So that really abstract notion about what a category is that comes in science, the kind of natural kind idea, that it's whatever is out there in the world that's causing this set of correlations among data, that actually seems to be what the 4-year-olds think that a category is, and not the idea of the distribution. I mean, you can show that they can detect the distribution from the time they're infants, right? So they are in effect doing the clustering, but their conception of what's going on with the clustering, even when you're 3 or 4 years old, is that it's this abstract underlying causal system that's actually giving rise. So the sort of Bayesian picture seems to be very, very, very deeply built into the way we're even thinking about categories.
Okay. Last comment.
So I guess the last comment I would say that it may be that in the trees that stand around us in understanding that AI will actually come in as more than one tree, and that there may be different ways that AI will function in that. It won't be just the AI tree and the differential equation tree and the analog model tree and so on, but that AI may stand in different ways and in different forms of clustering, in particulars in probabilistic distributions, and so on. I think we ought to remain open to that possibility too, that more than one AI in the image context will help constitute what we mean by understanding in 10 years.